So today we are expanding our portfolio of functions and their graphs by studying rational functions. And a rational function is just a ratio of two polynomial functions, p of x divided by q of x, where p and q are both polynomials. And when you divide two polynomials and you graph the result, you get something that looks nothing like a polynomial. So I'm going to show you the graphs of several rational functions so you get the idea of what these kinds of functions look like. And here's our first one, x plus 5 over x minus 3. And it doesn't look at all like a polynomial. Remember, the polynomials were our roller coaster graphs. They were always continuous from left to right, meaning we could draw them without picking up our pencil. And this graph is not continuous. It's got this big break in the middle. In fact, it's got these two arms to the graph that are completely disjointed. And I'm going to turn on this folder that says asymptotes, and it turns on these dotted lines. Now, these are not part of the graph, all right, but they are kind of boundaries for the graph. And these asymptotes, if I zoom out on this graph, these asymptotes actually show what most of this graph looks like if I zoom out far enough, right? So the difference between our graph and these two lines is only visible when we get kind of zoomed in here. All right, so the purple line is what we call a vertical asymptote, and the green one is called a horizontal asymptote. So the purple one, a vertical asymptote, is going to be this barrier. It's this invisible line that the graph just will not cross. The graph sees it coming and it splits off and will not cross the graph. And you might guess why the vertical line, the vertical asymptote for this function is at x equals 3. We'll get that officially written down a little bit later. The horizontal asymptote, though, is not a barrier. Although it looks very similar to the vertical asymptote on this example, we'll see a little bit later on that sometimes a rational function will cross a horizontal asymptote. The horizontal asymptote is more just like a guide for the right and left hand ends of the graph. And it just kind of tells the graph where to settle down to. So you'll notice that the end behavior of these graphs is not like polynomials where they were shooting off to infinity or negative infinity, starting high and ending low, that kind of thing. A rational function will flatten out towards some kind of line eventually. All right, so let's look at another one. All right, so here's our second rational function, and you can see that this one is broken into three parts. So rational functions can be broken into as many parts as their formula warrants. This one has got vertical asymptotes at 2 and -2, and again, that's going to show up pretty obviously in the formula. The horizontal asymptote for this one, that green dotted line, is the x-axis, y equals 0. All right, and like I said, you can see that it's willing to cross its horizontal asymptote in the middle. So the horizontal asymptote only holds sway over the graph at the very far ends on the right and the left-hand side. Those purple vertical asymptotes, though, those are hard and fast barriers that the graph never crosses. All right, here's our third rational function. Again, we've got a vertical asymptote that the function is avoiding at all costs. The horizontal asymptote, it actually crosses over at x equals -3 and at x equals 1. And this one kind of has a funny little hump that it goes up and over its horizontal asymptote before finally settling down at it. All right, this last one I showed you, this was of a type that we're not going to spend a whole lot of time on, but I just wanted to show you that this kind of thing does exist. This one has a vertical asymptote, but it also has what we call a slant asymptote. So it still has these two lines that if I zoom out, pretty much describe what the graph looks like, except they're in the middle. All right, but instead of being a horizontal asymptote, this one has a slanty asymptote. You can actually find the equation of that line pretty easily. We're not going to spend any time on that in our class, but I just wanted you to know that these kinds of things do exist. All right, so before we do any calculations regarding asymptotes, let's actually get these definitions written down officially. So a vertical asymptote of a rational function is an invisible line, first of all, that the function will not cross. Right? A horizontal asymptote is likewise an invisible line Okay, we saw that rational functions will sometimes cross their horizontal asymptotes, but again, the horizontal asymptote is not a barrier, it's more of a guide and just for the right and left-hand sides of the graph. Okay, so it's an invisible line that governs end behavior. So what I want to do for the rest of this video is to figure out how to calculate those vertical asymptotes just by looking at the function. All right, so you might have guessed as we were going through these pictures what was causing the vertical asymptotes. You can usually see it in the formula of the function. All right, so this graph had a vertical asymptote at x equals 3, and you can see in the formula x plus 5 over x minus 3 that 3 is the number that causes division by 0. And we can't divide by 0, and that's why vertical asymptotes are absolute barriers for graphs. You can't cross a vertical asymptote because you can't divide by 0. So you can see in the second function that it had vertical asymptotes at 2 and -2, and those are the two numbers in that second formula that cause division by 0. -2 makes x plus 2 equal to 0. X equals 2 makes x minus 2 equal to 0. So both of those cause a problem for this function, and that's why we have vertical asymptotes there. For our third function, the vertical asymptote is the y-axis, which is x equals 0, and x equals 0, 0 cubed down in the denominator causes division by 0. And even with our slant asymptote function, if you look at x equals -1, that's the number that causes division by 0 for this one. All right, so I've asked you in this example to calculate the vertical asymptotes of this function. All you have to do to find the vertical asymptotes of a function is to set the denominator equal to 0. So what makes this equal to 0? And this is going to feel a lot like what we did to find the domain of a rational function. And it's pretty much the same procedure. The notation at the end is just slightly different. Okay, so we're just going to take that denominator and set it equal to 0. It's an easy quadratic equation to factor. You can use the quadratic formula too if you're not a big fan of factoring. So x plus 4, x minus 1, set both factors equal to 0. And subtract 4 from both sides and add 1 to both sides. And so these are your two vertical asymptotes. Okay. And notice for vertical asymptotes that we didn't do anything with that numerator, that x plus 2, that can be anything that it wants. Vertical asymptotes are only concerned with the denominator. All right, in the next video, we will talk about horizontal asymptotes.